Okay, so in my previous video, a couple of while ago, we talked about complex numbers and we started to bring this lecture to life, if we will. I'm going to continue with that lecture today, and the way I'm going to continue with it is exactly where we picked it up last time round. I'm going to start today with a definition, so I'm going to crack straight on here with a definition. And that definition here says, if z is a complex number, and n is a member of the positive integers, that's what that sign means there, and z to the power of n is equal to 1, then we say that z is a root of unity. Now, we could possibly call that an nth root of unity as well. That's the definition. And this is also going to bring us to a proposition, and this is notated by proposition 7, which says to take z as a complex number, and then z is an nth root of unity if and only if the modulus of z is equal to 1 and the argument of z is equal to 2k pi over n for some integer k. Now, we talked about the modulus and the argument in a previous lecture. Again, I'm going to prove this thing, and the way I'm going to prove it, because it's an if and only if, I'm going to work from left to right first of all. So I'm going to suppose z is an nth root of unity. And then from the definition, we can say that z to the power of n is equal to 1, and then the modulus of z to the power of n is mod z to the power of n, which is equal to 1. And of course, the modulus of z is positive, it's greater than 0, so the modulus of z is equal to 1. And of course, by what we ended with last lecture with Demoivre, the argument of z to the power of n is n times the argument of z, so the argument of z then is going to be just equal to the argument of 1 over n, which we know is just 2k pi over n for some k in the integers. We prove it the other way. It's very, very similar. We're going to suppose that the modulus of z is equal to 1, and that the argument of z is 2k pi over m for some integer k. Then the modulus of z to the power of n is mod z to the power of n, which is of course 1. And the argument of z to the power of n is n arg z, which is 2k pi. So z to the power of n has the same modulus and argument as 1. So z to the power of n must be equal to 1. And then that, of course, completes the proof. So nice little remark here, which I think is quite clever, is that this proposition here, which is proposition 7 shows that the roots of unity lie in the unit circle, which the unit circle is defined by S1, as I said in the previous lecture. And this actually brings us to the corollary 8, which is a nice little result from what we've just proven. For n being greater than or equal to 1, there are exactly n nth roots of unity. Which sort of is common sense, but we're going to prove it anyway logically, just as we did before. So by proposition 7, the thing that we just did a moment ago, the nth roots of unity are they are the cos of 2k pi over n plus I sine of 2k pi over n for any integer k that we like. And so there are n such distinct values, i.e. different values, e.g. choose some k to be, well, the set of all 0, 1, all the way up to some n minus 1, for example. And that completes the proof. Which then brings us to this definition, which sort of is logical sense, but you'll see what I mean in a minute. We're going to let z be an nth root of unity, so using that definition that I started today's lecture with. So let z be an nth root of unity if z to the power of m is not equal to 1 for, for 1 being less than or equal to m less than m minus 1, then we say that z is a primitive nth root of unity. That's the bit I'm defining, so I underline it. And from this, that brings us to the next proposition, which is known as proposition 9, and which says if z is an nth root of unity for some n being greater than or equal to 2, and that the modulus, well, and that z is not equal to 1, of course, then z to the n minus 1 plus z to the n minus 2 plus all the way up to plus z plus 1 is equal to 0. Now, there's a key factorization here to basically give you the proof that we have that 0 is z to the n minus 1, just rearranging what we know for an nth root of unity. And if you factor out z minus 1, if you know this fraction very well, then actually what you get is z to the n z to the n minus 1 plus z to the n minus 2 plus all the way up to plus z plus 1. And z is not equal to 1, which is the key bit of my proposition here. So this basically drops out immediately, and that's the end of my proof. Okay, and this brings us to Euler's formula, which is a fact. It's a fact and not a theorem, because we're not going to prove it, because we don't have enough mathematics to prove it yet, up to this level. Once you've done analysis, you'll be able to understand this a bit better. But anyway, for theta being real, we have e to the I theta being cos theta plus I sine theta. Remark: this gives a very convenient way to represent a complex number if z has mod z being equal to r and the argument of z being equal to theta, and then z equals re to the I theta. And I'm going to put that in flashing neon lights to remind you that this way is very important and you should get used to it. Okay, so following that brings us to proposition 10. We're almost there now. Proposition 10 is to take z as a complex number, excluding 0. So in your own time, you might want to be thinking about why am I excluding 0 from this case. Then z has exactly nth roots for any n greater to 1. So the proof of this thing is not the easiest. So we kind of need to look at a few things. We need to look at, first of all, at least one nth root. So we're going to let the modulus of z being equal to r, and theta being, of course, the argument of z. So z is r e to the I theta by that fact that I stated a moment ago. And then there is a unique, positive, real s, such that s to the power of n is equal to r, since, of course, r is greater than 0, it's positive. I will make a note to see analysis if you don't know why that doesn't work, or why this works in this specific way. This is due to the supremum and the bounds, really, the boundedness of this s to the n equals r. The whole boundedness of this is basically what makes this work, essentially. So what I'm going to do is I'm going to let phi be equal to theta divided by n, and then I'm going to let w be equal to some se to the I phi, and then we're going to say, well, w to the power of n is equal to z. So that's only one case, but we need to look at least nth roots. These little bullet points are just how to structure your work. So I'm going to take w as written above, and then I'm going to let alpha be nth root of unity. Then alpha times w to the power of n will be equal to z. And of course, by corollary 8, there are n such alpha giving at least n distinct nth roots of z. The final case that we have to look at in the course of this proof here is to look at most nth roots. And this is quite similar. We take w as we did above, and we're going to let's pick u, I suppose. We'll let u be an nth root of z. Then w to the power of n is then just equal to z, which is, of course, just u to the power of n from our definition. So, and the fact that z is, well, non-zero, so w can't be 0. So, because I don't like dividing by 0, u divided by w to the power of n will be to 1. So u divided by w is an nth root of 1. And of course, by this corollary 8 that we've been using, there are n of these. So there are at most n choices of u. And that will complete the proof. So proofs at university are a bit more structured, in that we give these little bullet point starters to sort of help you on your way a little bit. Of course, I don't do this for every single proof that I do in the course, but I sort of help you along your way a little bit. Okay? Now, this brings us to a nice little proposition, known as Proposition 11, which is about polynomials, and says that a complex polynomial of degree n has, at most, n roots in the complex plane, in C. So, let's prove this thing then. The proof of this, well, by induction on n, which is, of course, the degree of the polynomial. So for n equals 1, that's a quick check. I'm not going to do n equals 1 because it's a bit straightforward. You should do that, though, in your notes. For n equals 1, then as we've got n equals 1, we can then, well, we just jump into it using our inductive stuff. So the inductive step is to, well, let P be a complex polynomial with some degree n, and suppose the result holds for polynomials with degree less than or equal to n minus 1, and then dividing by the leading coefficient there, well, that doesn't change the roots, does it, exactly? So we may assume that P is a monic polynomial. If it's monic, then the coefficient in front of the highest term will be 1, essentially. That's what this is. So if I sort of explain this in actual notation, P of x will be x to the n plus a x to the n minus 1, all the x plus a 1x plus, well, a0, i, for some a0, a1, all the way up to a n minus 1 to b and c. For any variable that you state, you should tell me what it is. This just goes for general mathematics and not just in the terms of in a proof. You should tell me whenever you're doing it. So you see a lot of symbols I'm using just because I don't want to keep writing out the same thing every single time. It sort of helps me along my way a little bit. And as I'm talking about here, the leading coefficient is 1. So, if P has no roots at all, then we're done. So, if P has some root alpha in the complex numbers, then P of x is equal to some x minus alpha times f of x. for some complex monic polynomial degree n-1, and of course with induction we conclude using by the inductive hypothesis. F has at most n-1 roots, and any root of P is alpha or a root of F, and so P has at most n roots, and that will complete the proof. Now, we are literally here at the end of this lecture, and I want to finish it with a theorem called Theorem 12. It actually has a name. It's the fundamental theorem of algebra. Now, so it says that any complex polynomial, and of course we talked about complex polynomials about a couple of minutes ago, any complex polynomial of degree n has exactly n roots, of course, counted with multiplicity, i.e. if they've got multiple roots of the same one, potentially. That is, if P is a monic complex polynomial with degree n, then P of x is equal to x minus alpha 1 all the way up to x minus alpha n for some alpha 1 all the way up to alpha n in C, which of course not necessarily distinct roots. The proof of this is not in this course. Well, it's definitely not in this lecture, without a doubt. You need ideas from complex analysis and topology to prove this theorem. So you need a lot more than what we're talking about here to actually use this. Now, you should only really use this theorem if you really have to and you've got nothing else to go off. Then you use this theorem. The proof of it is not the nicest, it's quite long-winded, and I would only probably teach this in a second, maybe third year module to sort of explain this. But this is just in here as you can use it, but you shouldn't really use something if you've not proven it. That's like a general rule in mathematics, where if you've not seen a proof of a theorem, then you should not use the theorem at all. You shouldn't quote it, unless you've seen a proof of it. Anyway, that is the end of my complex numbers course. A quick whistle-stop tour of complex numbers nonetheless. I hope it's been of use to you, and if you want to do more of these for any other topic, then do let me know. Thanks very much, and bye-bye for now.